Welcome, CSEC Chemistry, May 2024, Paper 2, Solutions for Questions 1 to 3. Subscribe for questions 4 to 6. Let's begin. Question 1. Sodium thiosulfate solution reacts with dilute hydrochloric acid to produce sodium chloride solution, sulfur dioxide gas, solid sulfur, and water. This experiment was conducted to investigate the effect of temperature on the rate of reaction. Below, you can see temperature readings that were measured. A. Define the term rate of reaction. Rate of reaction is the measure of change in the concentration of reactants or products over time at a given temperature. Or you could write the speed at which a chemical reaction takes place. B. Part 1. Write a balanced chemical equation for the reaction between sodium thiosulfate and dilute hydrochloric acid. Now here's the equation below, however it is not balanced. There are 2 sodiums on the reactant side while 1 sodium on the product side. Also, there is 1 hydrogen on the reactant side while 2 hydrogens on the product side. In order to balance this equation, we are going to write the coefficient 2 in front of the hydrochloric acid on the reactant side and 2 in front of the sodium chloride on the product side. Part 2. Describe a test and state the observation that can be used to confirm the presence of the sulfur dioxide gas produced from the reaction. We will be going through 3 possible tests. The first test is passing sulfur dioxide gas through acidic potassium permanganate solution. The observation will be the purple solution changes to colorless. Test number 2. Using damp or moist blue litmus test. The observation will be paper changes from blue to red. Another test that could be used is passing sulfur dioxide through acidified potassium dichromate solution. The observation will be the solution changes from orange to green. Part 3. Determine the mass of sulfur dioxide produced when 50 cm³ of the gas was collected at STP. Now the relative atomic mass were given for sodium and oxygen, and it also states that 1 mole of a gas occupies 22,400 cm³ at STP. First, we are going to calculate the relative molecular mass of sulfur dioxide. The mass number for sulfur is 32 plus the mass number for oxygen 16. However, since there are 2 in sulfur dioxide, we multiply 16 by 2. This equals to 64 grams per mole. 1 mole of sulfur dioxide occupies 22,400 cm cube. Also, 1 mole of sulfur dioxide is 64 grams. Therefore, 22,400 cm cube of sulfur dioxide weighs 64 grams. Then 50 cm cube equals to the unknown that we are calculating, x. We are going to cross multiply. The answer will be x equals 50 cm cube multiplied by 64 grams, and this answer divided by 22,400 cm cube. The answer will be 0.143 gram of sulfur dioxide. C. Part 1. In Table 1, record the temperature readings for each of the experiments shown in Figure 1 on page 4. Based on the thermometers, the smaller intervals represents 0.2 degrees Celsius. Experiment 3 is 14 degrees Celsius. Experiment 4, this is 20, 20.2, 20.4, is 20.6. Since it's in between, this is 20.5 degrees Celsius. Experiment 5 is 27 degrees Celsius. Experiment 6, 33 degrees Celsius. Experiment 7, 35, 35.2, 35.4. It's not at 36, it's in between, therefore 35.5 degrees Celsius. Adding the values to the table, that's 5 marks. Part 2. Calculate to 3 decimal places the rate of reaction for each experiment, given that the rate is 1 over time. Record your results in column 4 of Table 1. Experiment 3. 1 divided by 40 equals 0.025. This is already at 3 decimal places. Experiment 4. 1 divided by 24 equals 0.0416. Since 6 is greater than 5 in the 4th decimal place, we are going to add 1 to the value in the 3rd decimal place. Therefore, the answer is 0.042. Experiment 5. 1 divided by 15 equals 0.0666. Therefore, the answer to 3 decimal places is 0.067. Experiment 6 is 0.091. Experiment 7, the rate is 0.1. Since it's supposed to be to 3 decimal places, we're going to add 0 in the 2nd and the 3rd decimal place, hence 0.100. D. Part 1. Using the axes provided in Figure 2, plot a graph of the rate of reaction versus temperature. Draw a smooth curve through the points. First, I'm going to label the axes, the vertical axis Y and the horizontal axis X. Based on the scale for the Y-axis, we are going to deduce the value for each small line. 2 centimeters equals 0.010. Therefore, 1 centimeter equals 0.005. Each small line represents 0.001. So that's 0.001, 0.002, 0.003, 0.004, and there 0.005. For the x-axis, 2 centimeters equals 5 degrees Celsius. Hence, every 2 small space is 1 degree Celsius, 2 degrees Celsius, 3 degrees Celsius, 4 degrees Celsius, and there you go, 5 degrees Celsius. I will be explaining how to plot 1 point. Find 5 degrees Celsius on the x-axis, go up until 0.017 on the y-axis, put a dot and circle it. Plotting the points for all the experiments up to experiment number 7. Afterwards, draw a smooth curve through all the points. Part 2. Using the graph you plotted on page 7, explain how the change in temperature affects the rate of reaction between sodium thiosulfate and hydrochloric acid. As temperature increases from 5 degrees Celsius to 15 degrees Celsius, the rate of reaction slowly increases. As temperature increases above 15 degrees Celsius, the rate of reaction rapidly increases. Overall, as the temperature increases, the rate of reaction increases. Number 2. The most stable form of the element oxygen has a mass number of 16 and an atomic number of 8. It can also exist as a radioactive isotope. A. Define the following terms. Part 1. Atomic number. The answer is the number of protons in the nucleus of an atom. Part 2. Mass number. The definition: the total number of protons and neutrons in the nucleus of an atom. Part 3. Isotopes. Isotopes are atoms of the same element which contain the same number of protons but different number of neutrons in their nuclei. Therefore, the same atomic number but different mass number. B. Use a dot and cross diagram to show the bonding present in oxygen gas. First, write the letter O to represent oxygen, and then we are going to draw the valence shell, which is the last shell for oxygen. Since oxygen is in group 6, there are 6 electrons on the last shell. Whenever you are adding the electrons, place them north, south, east, and west. Oxygen gas comprises of 2 oxygen atoms. Therefore, we are going to draw another atom for oxygen. However, we will be representing the electrons using cross instead of dots. Oxygen is a non-metal, therefore the bonding will be covalent. Oxygen atoms are going to share electrons in order to have a complete octet, which is the maximum number of electrons on the last shell. The valence shells will overlap in order for each oxygen atom to have 8 electrons on the last shell. One oxygen will be sharing 2 electrons and the other oxygen will be sharing 2 electrons, as you can see in the intersection of the diagram. Or you could draw the valence shells touching, and wherever they meet, you place the shared electrons. C. There are many uses of radioactive isotopes in everyday life. List any 3 uses of radioactive isotopes. One of the uses is used in the creation of smoke detectors, americium-241. Used in medicine during radiation therapy to detect cancer, technetium-99m. Used in agriculture to kill pests, cobalt-60. Used to prolong shelf life of food, cobalt-60 or cesium-137. D. Carbon burns completely in excess oxygen to produce carbon dioxide. Write a balanced chemical equation including state symbols to show this reaction. So here we have solid carbon plus oxygen gas to produce CO2 gaseous state. This equation is already balanced since there is 1 carbon on the reactant side and 1 carbon on the product side. Also, there are 2 oxygens on the reactant side and 2 oxygens on the product side. E. Carbon burns in limited oxygen supply to produce carbon monoxide. Write a balanced chemical equation including state symbols to show this reaction. Solid carbon plus oxygen gas producing CO gas, carbon monoxide. This equation is not balanced since there are 2 oxygens on the reactant side and 1 oxygen on the product side. In order to balance this equation, we are going to write 2 in front of the carbon on the reactant side and the coefficient 2 in front of carbon monoxide on the product side. Question 3. A. Compounds A and B are straight-chain hydrocarbons whose molecular formulas are C5H12 and C6H14 respectively. Part 1. State 1 natural source of hydrocarbons. Possible answers are crude oil, natural gas, coal, or petroleum. Part 2. State 2 uses of compound B. Now, compound B is hexane. The use include used as a solvent, used in the formation of shoe glue, used to extract vegetable oils, also used as a cleaning agent in printing. B. Part 1. Draw the fully displayed structure of compound A. Compound A is C5H12. Hence, draw 5 carbons in a straight chain. Since there are 12 hydrogens, we are going to draw single bonds between carbons and hydrogens, ensure that all carbons have 4 bonds. C. Part 1. List any 4 general characteristics of a homologous series. Answers in no particular order. 1. Same general formula. 2. Same functional group. 3. Same chemical properties. 4. Members have a common general method of preparation. 5. Same last name ending. Part 2. Deduce the homologous series to which compounds A and B belong. Both compounds have the same general formula CnH2n plus 2. This formula is for the homologous series alkane. D. Compound B, C6H14, burns completely in oxygen to produce carbon dioxide and water. Write a balanced chemical equation, including state symbols, for this reaction. Here is the chemical equation. However, it is not balanced, since there are 6 carbons on the reactant side and 1 carbon on the product side. Also, there are 14 hydrogens on the reactant side and 2 hydrogens on the product side. Lastly, there are 2 oxygens on the reactant side and 3 oxygens on the product side. In order to balance this equation, we are going to write the coefficient or numeral 2 in front of compound B, 19 in front of oxygen, 12 in front of carbon dioxide, and 14 in front of water. Questions 4 to 6 will be posted, so subscribe and share. Thanks for watching.